Hello students, in today's session we are going to explore the front-end VLSI design, the stage where the chip is designed logically before it is physically built. Whenever you use a mobile phone, a laptop or an automotive controller, there is a complex chip inside. But before the chip becomes silicon, it first exists as an idea, then as an architecture and finally as a RTL code. Front-end design is the phase where engineers define functionality, write the hardware code, verify behavior, and ensure timing correctness. If the front end is strong, the chip will function correctly. If the front end has error, even the best fabrication cannot fix it. Let us now walk step by step through how the chip is logically created. Before entering into the session, please subscribe our channel. Let us start with the front-end design flow. Front-end is the logical design phase of a chip where functionality is designed, coded, and verified before physical implementation is done. In this front-end, we have totally 11 stages. Let us see all the stages one by one. The first stage is system specification. This stage, it defines the chip's functionality, performance targets, power budget, area limits, and interface requirement. Then the next stage is architecture planning. In this stage, it breaks the system into major blocks and defines the overall data and control flow. The next stage is microarchitecture design. In this, it details the internal implementation of each blocks using pipelines, FSMs, registers, and data paths. Followed by, we have RTL design, coding stage. Implements the design in the synthesizable HDL such as Verilog or System Verilog. The next stage is RTL simulation. This is the stage running the RTL code like Verilog, VHDL, System Verilog to check whether it behaves correctly. The next stage is lint checking and CDC, clock design crossing check. In this lint checking, it detects coding style errors and structural issues in RTL. Whereas in the CDC, it ensures safe signal transfers between clock design to avoid metastability. The next stage is functional verification. Here, it thoroughly tests the design to ensure the correctness across all possible scenarios. And the next stage is synthesis. In this stage, it translates the RTL into an optimized gate level netlist using standard cell libraries. And the next stage is formal verification. In this stage, it confirms the synthesized netlist is logically equivalent to the original RTL. And the next stage is pre-layout static timing analysis, STA. In this stage, it checks timing constraints such as setup and hold before physical implementation. The last stage is post-synthesis simulation. In this stage, it simulates the gate level netlist to verify functionality after synthesis. Now, let's go deep into each and every stages. Yeah, the specification stage is the foundation stage of the VLSI design. In this, product idea is converted into a formal engineering document. At this stage, we decide whether it is a processor, an AI accelerator, an automotive controller, a 5G modem, a custom SoC. This stage becomes a structured technical plan. Next, let's see what engineer defines. During this stage, engineers define operating frequency, power budget, area budget, interfaces like USB, PCI, DDR, SPI, and process node, whether it is 7 nanometer, 28 nanometer, or 45 nanometer, and operating temperature range. These parameters guide the entire design flow. Why the specification stage is critical? If the specification stage is incorrect, timing will fail in later stages. Power target will not be achievable. Area may exceed cost limits. Product cost increases drastically. And what are the inputs to the specification stage? The inputs comes from market requirement, customers requirement, previous generation chip data, cost target, and manufacturing constraint. What are all the outputs of the specification stage? At the end of the stage, we get functional specification document, performance targets, power and area targets, architecture planning document. These documents is handed over to architectural team for the next process. The next stage is architecture planning. This is the blueprint of the chip. In this stage, it divides the overall system into major functional blocks and defines how data and control signals flow between those blocks at a high level. What happens here? In this stage, the system is divided into major functional blocks. It defines data path and control path. It decides the number of cores and execution units. It designs memory architecture like cache and buffers. And it defines interface protocols like AXI, AHB, PCI, etc. And it plans pipeline stages and parallelism. This is where the chip's internal structure is decided. What they optimize? They optimize performance, power consumption, area, latency, scalability, and reusability. What are the inputs of architecture planning? The inputs are system specification document, performance and power budget targets, market requirement, previous chip architecture, process technology information. And what are all the outputs of this architecture planning? The outputs of this architecture planning are high-level block diagram, data flow and control flow design, microarchitecture guidelines, interface definitions, performance budget allocation per block. This output is handed over to the RTL design team. Architecture planning is where the real intelligence of the chip is designed. If the architecture is weak, no amount of coding can fix it later. This stage decides whether the chip becomes powerful or average. Microarchitecture design stage is the stage where the architecture becomes real hardware. It defines what the system does and how it works internally. This is the detailed internal implementation stage. What is designed in microarchitecture? Microarchitecture describes the internal structure of each block, including pipeline design, FSM design, data path structure, register organization, and execution unit. Every cycle level hardware detail is planned here. Then next, what happens in the pipeline design? Pipeline design, it decides the number of stages and balance speed versus complexity, handles hazards and stalls, improves throughput. What is happening in the FSM design? FSM is the brain controlling the data path. It defines state transitions, control data movement, and manages operational flow and handles conditions and decisions. Next, the data path structure. It is where the real computation happens. It defines the ALU connection, adders, multipliers, shifters, and data path bus width, that is whether it is 32-bit or 64-bit, and it tells the execution unit connectivity. Next one is register organization. Register organization, it gives the number of registers, registers with pipeline registers, and control and status register. Registers manage timing and data storage between each stage. The next one is execution unit. These execution units determine performance capability, and they give arithmetic units, logic units, memory access units, and special processing units. Why this microarchitecture is critical? If the microarchitecture is not designed properly, if it is poorly designed, then performance drops, power increases, area increases, and timing becomes difficult. A strong microarchitecture makes RTL design smooth. RTL design stage is the stage where the coding is written. Registered transfer logic stage writes hardware logic in HDL, either in Verilog, system Verilog, or VHDL. This is where the chip logic is actually written. microarchitecture becomes the real hardware code. What is the purpose of this RTL design? This is the heart of digital chip design. It converts microarchitecture into synthesizable HDL code. It describes hardware behavior using registers and logic, and it prepares the design for the synthesis. So what are the inputs we are going to give to this RTL stage? Clear architecture is equal to clean RTL. So the inputs are microarchitecture specification, block diagrams, timing goals, and interface definitions. What happens in this RTL design? In this RTL design, engineers write aware using Verilog or System Verilog or VHDL, and they implement adders, multipliers, ALU, FSM, etc. What engineers must be careful about? Here, the poor RTL will lead major problem in later stages. So, what engineers must be careful about is synthesizable coding style, proper reset design, clock domain handling, and timing awareness. What are the outputs of this RTL design? The output we get from this RTL design is RTL file, either .v or .sv, and basic constraint file .sdc. These files are then moved to the simulation and verification stage. RTL simulation is the stage where it simulates the RTL using test benches to verify that the design behaves correctly for different input scenarios before synthesis. The goal of this stage is to see if your design logic works as expected. The RTL is running your code and seeing the waveform output. Next, we are going to see Lint and CDC check stage. These are pre-synthesis quality gate. Before synthesis begin, we must clean the RTL. This stage prevents hidden design failure. So what is the purpose of this Lint and CDC check? They provide us clean RTL. They detect coding errors early, ensure synthesizable RTL. They identify unsafe clock domain crossings and improves overall design quality. What is lint checking? Lint is static code analysis process. It checks RTL for coding style violation, syntax mistakes, combinational loops, unused signal, multiple drivers. It improves RTL quality before simulation and synthesis. The next, why the lint is important? Without lint, hidden latches may appear, synthesis mismatch can occur, tool warnings increase, debugging becomes difficult later. So the lint catches problems early when they are easy to fix. Next, what is CDC? Clock domain crossing. CDC checks identifies signal crossing between different clock domains and asynchronous clock regions. Why CDC is critical? Improper CDC can cause random chip failure, data corruption, unpredictable silicon behavior. These bugs are very hard to debug after fabrication. The next, what CDC tool check? The CDC tool checks missing synchronizers, unsafe data transfer, multi-bit signal crossing issues, RDC, handshake protocol correctness. What are the outputs of this Lint and CDC check? Lint report warnings and errors, CDC violation report, and it provides clean RTL ready for synthesis. Only clean reports allow the design to move forward. The next stage is functional verification stage. This is the most critical stage in front-end VLSI. Writing RTL is not enough. We must prove that it works in all conditions. This stage consumes 60 to 70% of project time in the industry. So what is the purpose of this functional verification? When no verification is done, it is equal to risky tapeout. This stage thoroughly validates the RTL behavior and it ensures design works for all scenarios. detects hidden logic bugs, and prevents costly silicon failures. The next we are going to see is what is functional verification. Functional verification is testing the design with multiple input scenarios, comparing expected versus actual output, checking corner cases, measuring test coverage. The main goal of this stage is zero functional bugs before synthesis. Type of testing used here is direct testing and random or constrained random testing. What engineers check here? The engineers check correct data output, FSM transitions, protocol compliance, boundary conditions, error handling behavior. Every functional path must be validated here. The next one is we are going to see coverage analysis. Verification is not complete until coverage is high. The types of coverage are code coverage, functional coverage, branch coverage, and state coverage. Coverage ensures all scenarios are tested. After doing all this, what are the outputs of this functional verification? The outputs are simulation reports, coverage reports, bug tracking logs, and verified RTL ready for synthesis. After doing all these reports are given to the next stage process. Next, we are going to enter into the stage synthesis. Synthesis is RTL to real gate. RTL is just hardware description. Synthesis converts it into real logic gates. This is where abstract code becomes physical hardware structure. What is the purpose of this synthesis? This converts the RTL into gate level netlist. It maps logic to standard cell libraries and it optimizes for timing, power and area. This stage prepares design for physical implementation. What happens during synthesis? The synthesis tool, it translates RTL into logic gates, maps logic to standard cells like AND, OR, NAND, flip-flops, and it performs logic optimization, inserts buffer where required, and removes redundant logic. Every HDL statement becomes actual gates. What an engineer focuses on. Here, the engineers analyze setup and hold timing, critical paths, area utilization, power estimation, and constraint violations. So what are the inputs of this synthesis? The inputs of the synthesis are RTL file, that is the extension .v or .sv files. Then timing constraints, the .stc, and standard cell library .lib. Library defines delay, power and area of each gate. What are the outputs we get from the synthesis? We get gate level netlist, timing report, area report and power report. This netlist move to the physical design for the backend process. The next stage is formal verification stage, LEC, logic equivalence check. This stage proves that RTL is equal to netlist. After synthesis, we must ensure nothing changed logically, and this stage does that. What is the purpose of formal verification? Formal verification mathematically prove RTL and netlist are identical. It ensures no logic mismatching after synthesis, and it detects hidden synthesis errors, and it guarantees functional equivalence. Next, what is LEC? LEC is equal to logic equivalence check. It compares RTL design and synthesized gate level netlist, and it gives us whether it is mapped or unmapped. How it works? It maps RTL signals to netlist signals, and it compares logical structures mathematically, and it analyzes all possible input combinations, and it identifies mismatch if there are any. And Why formal verification is critical? Without this LEC, synthesized optimizations may change logic. Functional bugs may escape. Silicon failure risk increases. And the next, what are the inputs to this formal verification? We give RTL file, synthesized netlist, and constraint files. What are the output we are getting from this LEC? We get equivalency report, either pass or fail, and mismatched details if any, and clean netlist approved for backend. Once after checking LEC, we give the report to the next stage. The next stage is pre-layout static timing analysis. This is the stage timing check before physical design is done. Before moving to the backend, we must ensure that the design meets timing requirements. This stage verifies speed and stability. What is the purpose of this pre-layout STA? It analyzes timing paths in synthesized netlist. It ensures setup and hold requirements are satisfied. It identifies critical paths and it prevents timing failure later. So what is this STA? This is static timing analysis. Ensures design can run at target frequency. It checks timing mathematically, does not require simulation, evaluates all possible paths, and identifies worst case delays. What STA checks? This STA checks setup time violations, hold time violations, clock skew impact, path delays, and critical path. What are the inputs given to this pre-layout STA? The inputs which we are giving us synthesized gate level netlist, timing library.lib, and timing constraint.stc. And what are the outputs we are getting from this pre-layout STA? We are getting timing report, slack values, critical path reports, and violation summary. If it is positive slack, timing is met. If it is negative slack, timing violation. If it is negative slack, we can't proceed to the next step. We have to go back either to the synthesis or the RTL code and we need to make the changes. If positive slack, we can continue. The next final stage is post-synthesis simulation. After synthesis, RTL becomes gates. But does it still behave correctly? This stage tells that. This stage verifies functionality after RTL is converted into netlist. So what is the purpose of post-synthesis simulation? This post-synthesis simulation double check before moving to backend. Verify functional correctness of gate level netlist. So what are the inputs given to this post-synthesis simulation? We give gate level netlist, test bench, and optional SDF files. What are the outputs we are getting from this post-synthesis simulation? We get simulation report, functional comparison results, and bug list. Clean results allow design to move to physical design. Once after confirming that our gate level netlist is error-free, this gate level netlist constraint files will be given to the backend part for the physical design. Front-end VLSI is not just a subject. It is your entry into the semiconductor industry. The future of chip will run because of the logic you design in the front end. So, thank you students. To know more about physical design, that is backend part, please follow us and subscribe our channel.